Pleasure to add my thanks to those of others to the organizers. I've always found these meetings invigorating, both mathematically and personally. It's a great pleasure after a long hiatus to be able to travel and to see old friends. So thank you very much, Chip and Jim. They are deeply appreciated. My work is joint with Tony Hager and Joanne Walters-Weyland. And I'd like to give you an overview. In fact, I'll spend about the first half of my talk simply talking about other issues in order to provide a little context. The thrust of my talk is simply to augment the classical Yosida adjunction, which I think of as a bridge between geometry and algebra. In our case, geometry is represented by the circle on the left as the world of topology. In our case, instantiated as the world of completely regular frames. That's F, the category. And on the right, it's the world of algebra in the form of W, the same W that we've been hearing about. And the connections are, on one hand, the functor from left to right called R, that's Banaszewski's R. That's the functor which to each frame assigns the W objects of frame functions from the topology of the reals to the given frame. Okay, so I will make frequent mention of R of L, and that's what I mean by it. Okay. Functor in the other direction is the functor which attaches to a W object its frame of W kernels. K for kernels. Okay, so that's the setup. I will refer to this frame as the Madden frame, again, by way of a suggestion of Banaszewski. Seem to have a problem.
Just click inside the window and be not have to go back.
Okay. Well, all I propose to do is add to this picture a little structure on the left side, but not on the right. So what I'm going to do is talk about the adjunction between the category of uniform frames and W. Okay. I'll have time to define the symbols that I haven't already as we go along, but the question, of course, is what is the left adjoint? What is the nature of the arrow at the bottom going from right to left? So back to the classical version. This is, of course, the famous theorem of Madden and Vermeer from their seminal paper of 1983. In its full glory, it simply says that given a W object, one then has a arrow from the W object G into an R of L, which is universal among all such arrows, in the sense that given a test arrow from G into another R of M, there is an explanation in the form of a frame map, little m, which instantiates the test arrow theta simply by composition, right? G tilde is the image of little g under the mu arrow, right? So that's a member of R of L. And theta of G is simply the result of following G tilde with this magical frame map M, which we say realizes theta. So this is the format that we would like to have in the case of uniform frames. In the classical situation, of course, and in the presence of any adjunction, the attention is immediately focused on the fixed objects, right? So, for example, if you start with a W object and extract its Madden frame and then look at R of that, the question is, what have you got? Well, you've got a much bigger W object, which is of the form R of L. And the category of such things then becomes reflective in W, right? And the reflecting arrow is just the arrow from G into R of K of G. I'll have a lot to say about that because these are very interesting objects and that has been the subject of a good deal of research. On the left, the fixed objects are the Lindelof frames. It is a fact that the Madden frame or any W object is Lindelof. And so when you start at the left, the arbitrary frame pass to its R of L and then extract from it the Madden frame. What you've got is not necessarily the frame you started with, but is instead a Lindelof frame with an arrow into the original frame. And the status is that of a co-reflection, as is always the case, but it is a co-reflection which is unavailable in spaces, right? So this is parallel in form to the compact co-reflection, which one has in spaces, the checkstone compactification. But the interesting fact here is that although in frames we have a Lindelof compactification, if you will, we do not have it in spaces. So this is yet again a situation where the point-free approach gives one somewhat more freedom, right? And certainly more symmetry. But it does mean that from the point of view of W, we cannot distinguish between L and its Lindelof co-reflection. Because you see, O of R, that is the topology of the reals, is certainly Lindelof, and therefore any arrow from that into L lifts to an arrow into the Lindelof co-reflection. And so, in fact, R of L is the same as R of the co-reflection of L. So now I'd like to talk about the laundry list of characterizations in the literature of the R of L objects. Even in the spatial setting, this is a complicated issue. The question here is, what are the W objects of the form C of X for some X? And I don't know the answer to that. Tony has a number of papers which strike me as rather deep on this topic. My sense is that most of the interesting results in this direction are negative. Your first and second and third guesses are probably not quite right. It's a deep issue and one which has received some attention. In the point-free setting, there are some results. I'll describe them here briefly. The original observation is built in his path-breaking paper, Atomless Parts of Spaces, in which he points out that these objects are those which are closed under countable composition. Joe and I had a paper in which we pointed out that if you have a sub-object of some R of L, which is already complete with respect to ordinary uniform convergence, in other words, it contains all the bounded elements of R of L, then there is a convergence which can be articulated in terms of R of L called star convergence. I won't describe it here, but completion, Cauchy completion with respect to that means that you have all of R of L. There is yet another convergence, this time called indicated uniform convergence, which Tony and I proved completeness gives you all of R of L. This is a distant cousin of relative uniform convergence and is equivalent to ordinary uniform convergence on some canonical quotients. And finally, here's a kind of a funny and recent result of Tony and mine. You can say that a particular W object is all of R of L if it's uniformly complete, of course. But it also must have the following interesting property: every large element. Where large here means that it generates the entire W object as a W-kernel. Every large element must have a multiplicative inverse in the partial multiplication on D of X. D of X is the X that Brian was talking about, the classical Yosida space. You have there not a total multiplication, but a partial multiplication. And the condition here is that you must have inverses for these big elements. Anyway, my only point here is to point out that it's an interesting and rather complicated issue as to when a particular W object is the R of L. Okay, and now I'd like to shift focus a bit. This is again all in the direction of deep background, and talk about what I think is, to me, the most amusing aspect of calculus in R of L, and that is the fundamental role played by pointwise suprema. To me, it is the height of irony that in the pointwise world, the most important concept is pointwise suprema. And I'd like to introduce this topic by reminding you that the order in R of L is determined by the behavior of the elements under evaluation at right rays, right? So this is the real numbers from R on up. And the observation here is that you can tell when one of these functions lies below another one simply by examining where each function takes this right ray. The smaller function takes that right ray. I say the function, what I really mean is the inverse of the function, the frame map associated with the function. Takes that right ray to this chunk of the domain, whereas the larger function takes that same right ray to this larger chunk of the domain. Yeah. So the theorem is that in R of L, F is below G if and only if that is true for each right ray R, right? That's just an easy calculation. But it now leads to the definition of a pointwise supremum. What does it mean to say that a sequence of functions has a particular F, say Fn, right? The functions are the Fn's. What does it mean to say that they converge upwards pointwise to a limit F0? Well, what it means is that the approximations take a particular right ray closer and closer to its destination under the pointwise join. That's literally what you mean when you say that a supremum is pointwise, right? This has to be a set theoretic union. Therefore, it has to be visible in the underlying frame calculation, right? So there's the definition. It's a purely frame theoretic definition, and it gives you a tool to calculate an R of L, which is absolutely fundamental. And it's fundamental for the following reason. You see, when you're dealing with a W object, some joins can be rendered incorrect by embedding the object in the larger W object, because you introduce the possibility of an interloper, something which is above all the approximations and below the alleged join. It turns out that it is precisely these joins which are incapable of being falsified in that way. So these are the joins which are context-free, which cannot be rendered incorrect by passage to a larger W object. So in that sense, they actually have a characterization which is free of the representation. No. But in any case, they're the important joins. They are in some sense absolute. Okay, and now I'm going to go briefly through, again, a little bit more of the arithmetic in here in R of L. There are three types of sequences which I'd like to introduce. One is what I'm calling a truncation sequence. This is a sequence, again, these are all in R of L, and the elements are assumed to be positive, with a feature that the nth term of the sequence is the truncate of the n plus first by n, right? That's the definition. But part of the definition is that the join of the members of the sequence at the left rays, right, should be pointwise up to the top, right? The second type of sequence is Mundaji's good sequences. These are the sequences which Mundaji used in his very famous result that MV algebras are categorically equivalent to unital abelian L groups, right? And these sequences are characterized in our context by the feature that the nth term is identical to the result of adding the nth term to the n plus first, and then the infimum with one. So as opposed to the first type, these are all bounded by one. So these are all bounded functions. And then the third type of sequence has this condition. I won't say more about that. But it also is linked. That is to say, the nth term meets only the n plus first term and the n minus first term and no others. So it's not quite pairwise disjointness, but the odd terms are all pairwise disjoint and the even terms are all disjoint. Okay. Notice that each type of sequence has, as part of its definition, something involving a pointwise join or a pointwise meet. This convergence to zero here is simply the assertion that the sequence declines and that the pointwise meet must be zero. Well, I'm hiding the truth here, but here's the truth. The truth is that anytime you have a positive element of RL, it truncates with the constant functions, give you a truncation sequence. And conversely, if you start with a truncation sequence, you always are guaranteed to have a pointwise join existent in R's RL. And that pointwise join has the original sequence as its truncates. Furthermore, every good sequence results as the differences of the terms of a truncation sequence. And therefore, given any good sequence, you can build from it a unique truncation sequence and then get a unique member of R plus L. And ditto for the sawtooth sequences. I won't go to that, but the point is, these are simply articulating the canonical methods of decomposing a positive member of R of L into three very useful types of sequences. The latter two being particularly useful because they're bounded. Right, that will become useful. Why? Because, oh, and by the way, the point of this slide is simply that you can reconstruct a given positive element of R of L by means of any one of its sequences. In the first case, it's simply the pointwise join of the truncates. In the second case, it's the pointwise sum, if you wish, that is the pointwise join of the partial sums. In the third case, you have to introduce a multiple here of the to sum the sawtooth sequences. But the point is, these are simply three different ways of decomposing a given member of R plus L. And then my favorite way of thinking about when a particular W object is all of R of L is just to say that every good sequence has a pointwise sum in the sense of the previous slide. Or alternatively, every sawtooth sequence has a pointwise weighted sum in the terms of the previous slide. I like that because I think it's somehow intrinsic, right? At least if you give me pointwise convergence. Okay, so finally, let's talk about the subject of the talk, right? I have to briefly remind you of what a uniformity is, and I'll do that in as quickly as possible. A cover of a frame is nothing more than a subset which joins to the top. One cover refines another if every member of the finer cover is contained in a member of the coarser. For a given cover and a given element, we can form what's called C times A. What is that? Well, that's just the join of all the members of the cover which meet A. So typically you think of a cover as a large collection of very small sets. So what you're doing here is you're pumping up A by augmenting it by means of everything which intersects it in the cover. So you're blowing A up just a little bit, and the fineness of the cover will determine the extent to which you increase it. We say that a cover star refines another if the set of these puffed up elements from the cover itself is a refinement. So this is a stronger sense of refinement than the unqualified version. We say when equipped with a family of covers, the little u is now to stand for a family of covers, that one element lies u below a second, if there is some cover in the family such that C times B, in other words, B blown up a little bit by C, still lies below A. The symbol I'll use here is the rather below symbol subscripted by U, and I do that intentionally because it turns out that in the situations that we're involved with, this less than relation interpolates. And therefore, it is a subrelation of the completely below relation. So it's supposed to remind you of that. The notation is supposed to remind you of that. So here's the definition of uniformity. It is simply a filter of covers in the refinement order. So you require that to the common refinement of two uniform covers should be uniform. And further require that every cover should have a star refinement, which is in the uniformity. And then you recover, the last thing you require is that every element be the join of those elements which are U below it. That last requirement is called admissibility. The uniform frame is a frame equipped with the uniformity. I will designate the uniformity by subscripting it with the name of the frame. And a frame homomorphism is said to be uniform if it takes covers to covers. So that gives us then the category UF of uniform frames and uniform frame homomorphisms. Here, I'd like to pause to say that the theorem, which is well known in spaces, is also true here. And it puts an exclamation mark on this topic, it seems to me, because what it really says is that if you live in the world of completely regular frames, as I do, then you really should understand that there is an implicit, there's some sense in which the uniform structure is present already, whether or not you acknowledge it, whether or not you use it. The fact is, you have it. What about covers? Well, we're going to say that a cover is principal if it comes from a cover of the real numbers by way of a frame map. Right? That's a principal. It's linked if it's indexed by Z in such a way that the adjacent elements may intersect, but otherwise the elements are disjoint. Two elements which meet non-trivially have to be adjacent in the indexing. Every principal cover, or that is every cover which comes from an R of L, is refined by one of these linked cozero covers. Why? Because that's true of the real numbers. Every cover with real numbers is refined by a linked cozero cover. So we will say of a uniformity that it is real if its uniformity comes from principal covers. The uniformity is generated in that way. And this now becomes a coreflective subcategory. So every uniform frame whatsoever has some part, some smaller coarser uniformity, which arises in this fashion. The canonical uniformity on the real numbers is the metric uniformity, and there the basis is if the covers of the form C sub k. I'll use that symbol, the family of all intervals of width at most k, 1 over k, excuse me. For a uniform frame, then I will form U of L as the W objects, all those frame maps from the topology of the reals into L, which take metric covers to a cover in L. So those are the uniformly continuous functions. This is, interestingly enough, a perfectly good W object, and in fact a vector lattice, but it is not a ring. So it's a situation where we study W, we study this subject in W, not because we're ignoring the ring structure, but because we don't have the ring structure. This is a functor. So now the only issue that I've got left on my campaign to complete the diagram for uniform frames is to describe the functor on the bottom of the picture, which goes from right to left. In the classical case, without uniformities, we called it K to stand for kernel. The next letter in the alphabet is J. So J is, for our purposes, going to be the functor, which does the following. Let me start at the top of this slide. You see, whenever I have a subobject of R of L, there is associated with it that uniformity, which is weakest with respect to making those elements of R of L uniform. This is Isbell's mu sub C, right? I'm going to call that U sub G. What are the covers? Well, that means that the base covers are all G of CK for some G in cap G and some CK of the form I described on the previous slide. And so these are the covers which can be defined by a finite mean of those guys. Anyway, that's the description of what I'm calling U sub G. It's the uniformity generated by G. Okay. It happens that as long as G is big enough, this thing is admissible, and big enough here means that you have to have enough elements of G so that their co-zeros join generate G. And then you have enough to make the uniformity admissible. Okay. Okay, so the full description of the functor J is that from a given W object, it extracts the Madden frame and equips it with the uniformity on the Madden frame generated by the image of G in the Yosida representation, G tilde. Be more. So we filled in the diagram. That is, we've identified both the functors U and J. Do we have the theorem? Yes. And the theorem is the same as before, except that the arrow now goes not into R of L's, but into U of L's. Okay. For every W object G, we have a arrow into U of L. We have a uniform frame L and an arrow into it, which is universal among all such arrows. So then the question is, okay, what are the fixed objects? And I'll start this time on the left. The fixed objects on the left are the Lindelof frames, which are real, right? Lindelof because when you apply our J functor, you are extracting the Madden frame, and real because you are extracting the uniformity generated by G, right? So that turns out to be co-reflection in uniform frames. The interest then focuses on the right side of the picture. What are those objects of the form U of L? Let's see. This is just to say out loud what I said before. This is a co-reflection. And on the right-hand side, we have a reflection. It's not surprising. But to describe this reflection now, I've got to go a little further, right? This is the part which in the classical case had a laundry list of conditions. I don't have a laundry list, but I do have one or two. They're based on the notion of what's called a finitely equi-uniform sequence. So what is that? Well, it's a sequence of members of U of L. So these are uniformly continuous frame maps on the topology of the reals. But they have a uniform property in the sense that for any K, that is for any CK, you can find a single cover in the uniformity, which refines the cover generated by the members of the sequence for all n, right? So the same C refines Fn of CK for all n, and that's the equi part in the equi-uniform definition. So it's the uniform, it's the condition for uniform continuity, but it applies uniformly to all the members of the sequence at once, right? And then one shows that in terms of the arithmetic of R of L, if you then focus on a particular element of R of L, and by the way, on this slide, the U's should be R's, not U's. But if you have just any member of R of L, and you look at its truncation sequence, its good sequence, and its sawtooth sequence, then the element is uniform if and only if all three of the associated sequences have this equiuniformity property. So here you see, it means that we can start with bounded elements in either the good or the sawtooth sequences and simply ask the question of whether the sequence of those gadgets is equiuniform. If the answer is yes, then we know that the continuous function in R of L that you build is also uniform. And so the theorem is simply that that is the only condition that I have at present for whether a particular subobject of U of L is all of U of L. Condition is simply that every equiuniform truncation sequence should have a pointwise join, or in the case of a good sequence, if it's equiuniform, it should have a pointwise sum, or if it's a sawtooth sequence, it's an equiuniform, it should have a pointwise weighted sum. Okay. Now, what do I have left?
Yes, it's about 9 or 10.
Let's talk now about some of the intrinsic qualities of uniform frames, most important of which is what's called completeness. Right? Whole point of uniformities is to routinize the process of completing an object, in this case, the underlying space or frame. But it turns out that there are two competing notions of what completeness ought to mean for frames. The more satisfactory of the two is the one I have here on this slide. A uniform frame is said to be complete if any dense surjection onto it, which is also onto the uniformity, is an isomorphism. Now that may not ring bells for you, but turn the arrows around. What that's saying about a space is that a uniform space is complete if every dense embedding is an isomorphism. You have to agree that's a dynamite definition of what you ought to mean by completeness. The other version of completeness, of course, is that every Cauchy filter converges, and we'll get to that in a minute. But let's start with this one. So the question I would like to address is, what then is the completion in the sense, and oh, by the way, it is a theorem in the topic that the complete objects are coreflective. And I will use chi for the coreflector of L, and I will use script C for the coreflection. Yeah. So C of L is the completion, and the map which takes the completion onto L is chi sub L. Okay. So the question is, what does one get as the completion of the J of G? Right? What is the completion of J of G? Well, this involves an excursion into the compact situation, so I thought I would briefly mention the situation in the compact case. Banaszewski and Gilmore established that, in fact, it's well known long before this paper, that a compact frame has a unique uniformity, and that is the uniformity generated by the finite covers. Okay, not only that, but the compact frame is always complete in its one and only uniformity. And in fact, the way that you get this compactification, this, by the way, is the uniform version of checkstone compactification, right? Is the compact co-reflection in the uniform context. The way you build it is exactly the way that you build the compactification in the classic Banaszewski-Mulvey construction of beta L. That is, you simply take the round ideals. Okay? The difference here is that round means round with respect to this uniformly below relation that we were talking about. So a uniformly regular ideal is simply an ideal with a feature that whenever you have an element in it, you have another element which is uniformly above, also in the ideal. And the Banaszewski-Mulvey construction works flawlessly to render the same conclusion here. That is, along with the join map, this is in fact an instantiation of the Samuel compactification. Okay, so we have this map L at present, thinking of that as being the J of G. And we're after C of L. We'd like to know what that is. And we have S of L, this Samuel compactification. But we know about S of L that it's compact and therefore complete. And therefore, it has to factor through the completion. So we have this little triangle simply by virtue of the definitions, right? And okay, so I repeat, this is the L is the Madden frame of some G, of some W object G. S of L is this rather interesting compactification, and we're after C of L. Well, the fact is, and this just imagine, you have to sort of go into a trance and look at the details. But the conclusion is that the C of L is carried by L itself as a frame. But the uniformities are different. The uniformity on L, as we mentioned before, is the uniformity generated by G, right? L here is K of G. And the uniformity that we decided to assign to it is the uniformity generated by all of G. And it's not complete with respect to that uniformity, mostly because the unbounded elements screw things up. But if you simply remove the unbounded elements from the generation of the uniformity, what you get is the completion. So that, I think, is new information. Now I'd like to mention the only other topic which I think we have by way of significant results, and that involves an excursion into territory that Brian outlined for us. Let's take a look at the J of G star here. What is that? Well, that's the Madden frame of the bounded part of G. And if you think about it, that's exactly the topology on the Yosida space of G. That's the space that Brian had been was working with in his entire talk, right? That's home base for Tony. Okay, that's a perfectly respectable uniform frame, and therefore, being compact, it factors through the Samuel compactification, right? So we have that arrow. And what that means is any frame map from the topology of the extended reals will, of course, lift to a map into the into JG star by virtue of the Hager-Robertson representation theorem. This is exactly the Hager-Robertson representation. But then we get an automatic bootstrap up into this richer compact frame. And by the way, these two frames are not the same. Here, you have what you get then is a representation of G inside D of this guy. Right? Brian talked about a representation of G inside D of this guy. We've now got a representation inside D of this guy, and they are not the same. This has some extra points, right? So here, the representation separated points. Here, it no longer separates points. Nevertheless, it's fascinating because it's closely connected to G. And at the end of the talk, I will give you some homework to produce an example in which you can really see the extra points. So the last point I'd like to make in this talk is simply that, and I mentioned it before, what's the deal with the Cauchy filters? Well, it turns out that the space of Cauchy filters on this uniform frame associated with the W objects is nothing more than the intersection of the domains of reality of the elements of G when it is represented in this new way, right? So we've got G represented as some extended real valued functions on the Samuel compactification. And you may or may not have an intersection of the domains of reality, but whatever you got, that's the space of Cauchy filters. So you see, it's easy to produce examples in which there are no such points. There are lots of W objects, which in the standard Hager-Robertson representation have no points common to all the domains of reality. It's easy to produce, and just as easy in the case of the Samuel representation. And this makes the point that the type of completeness here is rather weak. The second type. Thank you very much.
So this was sort of towards the middle, not the end. You're taking a W object and then you're taking the uniform elements, and you said that was an L group, not necessarily a ring. And that's sitting inside of R. How is it like fitting in there? Is it?
You have a representation of the entire W object in any case, right? And you do that by brute force. You simply put into the uniformity everything that you need to make all the members of the W object uniform, right? So the representation is perfectly satisfactory. And the only novelty here is that the target is a different object, right? It's the U of L as opposed to.
No, I think I was beaten before that, where you started with some object G, but then you took the ones that were frame homomorphisms, which were uniform, and that formed another W object. And maybe I misunderstood. Maybe can you go back like maybe 10, 15 pages? You go. Maybe the previous one. Maybe, or it was that one. No, I go forward. I'm sorry. That, no, previous, that. So this is the set of uniform frame homomorphisms, right? So you start with the uniform frame L, you take U of L. I'm guessing this is sitting inside of RM. Yep. So that's my question. Like, how is this sitting? It's not necessarily a ring, but is it thick?
You know, I've really got to give you your homework.
All right, please.
Right. Because there's a nice example that I think helps me understand the very question that you just asked. Take, don't write any higher than this, okay? Take, you're gonna go from -1 to 1. And look at the function 1 over x. Okay, and let the W object be, and this is close to your construction, a set of all functions on -1, 1, which are of the form h plus r over x squared. Okay. Where this is simply a member of C of -1, 1. This is a member of real numbers, okay? So in other words, take any real valued function on -1 and 1 and add a multiple of this to it. That gives you a very nice W object, right? What do you, when you then pass to, well, and the Madden frame of this guy is just the punctured interval, -1, 0, union 0, 1. Right? That's easy to see. Okay. But so this the Yosida space in the sense of Win is just -1, 1, right? But the Samuel compactification adds a whole bunch of additional points in here. For instance, when you now pass to all of the uniformly continuous functions, you pick up functions which approach infinity somewhat slower. For example, you pick up 1 over absolute x, but you don't get functions which go to infinity faster, such as 1 over x to the 4th. You don't get that. So there's something very subtle about the completion that we're trying to get hold of here, right? It's captured by that condition. You have to have this is really a fascinating example. So if you have some time to kill, it's worth your effort to sit here and convince yourself that first of all, that you have some additional points in the Samuel compactification, and second of all, that you really can approximate the one and you can't approximate the other. It's really very, very interesting in my opinion. This is a richer structure, which is quite a bit less than all of RL, quite a bit less. And it all depends on how you build these functions. You do it by taking these good sequences and combining them. But the kicker is that the sequence itself has to have this funny equiuniform property. And that really ties your hands as to what you can build out of it. You can build the one function that ascends more slowly, but not the other. It's really interesting.
So the question is kind of general, but what would happen if you change the unit? You got a W object with a selected unit, and as you were thinking about in your talk, thinking about does the uniformities, does the choice of unit alter uniformities?
Certainly would, right? I'm thinking it certainly would. Right, that screws up the initial classical representation, of course. Usually just by a multiplication. In most cases, you can get the two to commute with a multiplication, but I'm not sure, right? I'm not sure. Good question.
People set out to find the general theory of change of unit.
Yeah, no, turn your brain.
Anything else? Well, let's thank Rick Brown.